By popular demand, we are looking at Joseph Newton's Cursed Units 2 Cursider Units. For those of you who don't know me, I'm Tyler Foltz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
After posting my previous video on cursed units, and after it got a massive spike in views for no discernible reason, I discovered that kilowatt hours are extremely polarizing. A lot of commenters argued that kilowatt hours was a perfectly sensible unit for ordinary people who measure their appliances in watts and hours.
Well, I guess that answers that. Yeah, it shows up pretty often, and even outside of nuclear power, by a brick brain.
The alternative unit, megajoules, is much less intuitive. But there were also a lot of other commenters who sympathized with me, saying they had given the same arguments to their friends and family and were treated like lunatics, and that the oppressed joule appreciators should rise up against cursed units.
Now, megajoules, where have I heard that meme?
Can you match 50 million megajoules of lasing power, General?
Oh, and by the way, to give you a sense of scale, 50 million megajoules, or 50 trillion joules, is comparable to the atomic bomb that was used on Hiroshima, which is about 63 trillion joules. So while I don't hear megajoules as often as I hear kilowatt hours, they definitely sound cooler.
The truth is, I actually don't feel strongly one way or the other. I just find it fun to play around with notational standards given to us by history and make a caricature out of it. My goal is to teach you something about mathematics, not to claim that these are signs of societal dysfunction. Wait a second. People were saying they've seen kilowatt hours per 1,000 hours.
I mean, that's true. The thousands cancel each other out, and the hours cancel each other out.
Isn't that just watts? Wait, I need to check this for myself.
Yep.
You're up!
That's amazing.
The best explanation of this I've found is from a user on the Electrical Engineering Stack Exchange, who suggests that for a long time people conflated wattage with light bulb brightness. This meant that
I remember that, and I still see that on labels of light bulbs, especially in the US, which we all know is a sterling example of cursed units by not using the metric system, that it shows lumens and also watts based on what it would look like if it was an incandescent bulb instead of an LED. Strictly as a marketing tool. Hey, you gotta know your target audience, right?
when converting from older incandescent bulbs to more efficient LED bulbs, someone might swap out their old 40-watt lamp with a new 40-watt LED lamp and get flashbanged. So manufacturers describe the brightness in watts and the efficiency in kilowatt hours per 1,000 hours. This, of course, would never have been a problem if anyone cared about lumens or candela, the actual units for brightness.
Fascinating, isn't it? How you're kind of converting things in context for people that use the engineering units.
But you know what? It simplifies nicely, so it's not the worst. There's also kilowatt hours per annum, which is what my fridge has. That's seconds, hours, and years all in the same unit. You know what else was polarizing in the last video? The music. And I intend to keep it that way.
No problems with music, man.
Anyway, here's some more cursed units. The radian is a unit of angle such that 360 degrees is equal to 2 pi radians. This is so that if you have a circle with a radius of 1 unit of length, let's say 1 meter, then an angle of x radians subtends an arc length of x meters along the circumference. That's pretty neat, and what's also neat is that if the radius of the circle changes, then this arc length changes proportionally. So we could think of a radian as being 1 meter of arc length per meter of radius. A meter per meter. So
length divided by length, so dimensionless, right? Or it's just a ratio.
So a radian is just 1. When units completely cancel out like this, we call them dimensionless. Radians are quite special here. If we used a different measure of angle like degrees, we would get a different number. The fact that the radian is the unique angle that gives 1 is the reason why in mathematics we commonly assume that everything is in radians and don't write any units for angle at all. This has some weird run-on effects.
I can understand why mathematicians do it, but I'm used to seeing units.
There are angular versions of momentum and force, which are called angular momentum and torque, and since these depend on the radius as well, they pick up an extra unit of length. If we continue ignoring radians, then torque inexplicably has the same units as energy.
That's amazing.
There's also a 3D variant of radians. A steradian is a solid angle subtending an area on the surface of a sphere equal to the square of the radius. So by the same reasoning, steradians should be measured in square meters per meter squared, which is a different thing, but also the same thing.
That's awesome. How you can be in different dimensions and have the same thing. All right, that's pretty cursed.
But are radians really dimensionless? I don't think so, because there's another conflicting way that we could make angles dimensionless. Just take the number 1 to be 1 revolution. This is the more sensible option for describing the frequency of something rotating.
Okay, yeah, I mainly think of it like in terms of RPM, like engine speed, for that sort of thing. Never really thought of it in terms of radians, though. It's interesting. I love this. It's kind of exploring different ways of looking at interconnection of concepts that I already know, which I think is beautiful or cursed. Both, really.
Where we use units like RPM, revolutions per minute. So we have 2 different standards, which are off by a factor of 2 pi, and this results in 2 pi's popping up all over the place in any equations relating to rotation.
It'd be nice if pi's would just pop up, then you can have pi whenever you want them. Sorry, that was terrible.
So angles aren't really dimensionless, we just like to pretend that they are.
So this sort of thing reminds me of one concept in nuclear engineering, and that is looking at burnup, which is a weird concept in general. It's measuring essentially how much fuel you used in your nuclear fuel cycle. So a typical nuclear fuel cycle is about 18 to 24 months. But you can't necessarily just measure in time. Like, let's say you had to power down for some reason, because usually a time assumes you're at 100% power within commercial operations, which is your ideal case. You're at full power, making as many megawatts as you can. But when looking at where you are in a fuel cycle, you actually look at something called burnup. And the units of that are megawatt days per metric ton of uranium. So megawatt day, I know I've already talked about kilowatt hours and megawatt hours in the previous video. It's exactly what it sounds like. You're just multiplying it by a day instead of an hour, which in seconds, a day is 86,400. So megawatt day figures out to 86.4 billion joules. So you have energy, a megawatt day, dividing by the energy in a metric ton of uranium. Energy divided by energy. Now, the interesting thing is metric ton of uranium is not a constant because enrichment depends a little bit on each reactor's individual fuel loading and its fuel cycle. It's usually shown in the context of a Scrabble board looking thing like this because each fuel assembly has slightly different enrichment because you want to optimize your fuel loading and your heat distribution profile. Now, the highest number you could possibly hope for is using 100% uranium-235, which you'd never see in a reactor. A reactor is on the order of 2 to 6%. At the plant I worked at was on the order of 3 to 5, but those are the main ranges of enrichment you're working with in most nuclear power plants. There are exceptions, of course, such as the CANDU reactor that uses natural uranium. But 1 ton of straight uranium-235, which you're not going to see, not even in a really big nuclear bomb, not even in a submarine where you're dealing with higher enrichment, is about 8 times 10 to the 16th power joules. But you're not going to see numbers anywhere close to that for a commercial nuclear reactor. But you're having energy divided by energy in this case. And probably one way to make this even more cursed, though, is, at least in the US, it's written MWD divided by MTU, being metric tons of uranium, because this is what happens when Americans try to use the metric system. I have no idea why it's written that way, and it confused me quite a bit the first time I saw it written down.
But now let's look at a unit that is dimensionless, but we like to pretend that it isn't. A mole is a unit of quantity equal to the number of atoms in 12 grams of carbon. If you're thinking, isn't that just a number? You're correct. It's called Avogadro's number, and it's approximately 6 times 10 to the 23. Despite the fact that the mole is very clearly
it's a pretty big constant.
Dimensionless, it's still counted as an SI base unit. The perpetrator here is chemistry, and when it comes to shoddy units in chemistry, trust me, the mole is the tip of the iceberg. First, let me state that while you can multiply, divide, and take powers of units, more complicated functions like exponentials and logarithms only apply to dimensionless quantities. You can see
one thing I'd like your thoughts about is, do you feel like exp parentheses is more cursed than writing the number e raised to something? Because they're the same thing, it's just written differently. To me, exp looks weirder, but maybe that's just me.
See this in complicated equations in other areas of science. The units have to cancel before we can apply weird functions to them. After all, it doesn't make sense to take the logarithm of a liter, right? Except that's exactly what pH is. The acidity of a solution in water is determined by the concentration of hydrogen ions. You need to measure this in moles per liter and then take minus the base 10 logarithm of that, and that's the pH. So what's actually going on here is that we're secretly dividing by a constant 1 mole per liter to make the units work out. And this is very important, because if we measured the concentration in different units, we'd have to convert this 1 mole per liter to those units as well.
Yeah, I remember this, and this is... So you'll see this when, like, chemistry technicians take pH, at least the ones I've worked with, they would always convert to the metric units. Even if they typically take samples and measure it in gallons, they would just convert it because they'd use equations like this to measure the pH. But yeah, it's pretty weird. I've also never seen anyone really use the analog to pH, the POH, where you're looking at how basic or caustic something is.
This is why the whole study of dimensional analysis exists. When you conflate units, you get the wrong results. Chemistry literature has a bad habit of randomly forgetting figures of moles per liter, which makes the dimensional analysis really annoying. This all culminates in the reaction quotient, a quantity which, by some interpretations, has different units depending on the chemical reaction.
Yeah, and I think now we're getting back to metric tons of uranium again, because we're depending on what your enrichment is, because it's not a standard unit. By the way, another way of looking at that same concept, except it isn't displayed as a ratio, is effective full power hours or effective full power day. That one to me makes a little bit more sense than megawatt days per metric ton of uranium, because the ratio doesn't really add anything else, because they're both units are dependent on your enrichment anyway. And effective full power hours, I don't necessarily have to be running a conversion in my head when I just see that number.
Now, apparently the pH of pure water is 7, and this figure confused me for a long time. pH is determined by the concentration of hydrogen ions in a solution, but surely pure water doesn't have any ions, right? Well, as it turns out, water self-ionizes, meaning water molecules randomly split up into ions and then randomly recombine. The presence of these temporary ions is what gives water a pH of 7. But why 7? What's special about 7? Wouldn't that change with temperature or pressure? Well, it turns out the pH of pure water is exactly 7 when the water is somewhere around 24.87 degrees C. So the choice of 7 as neutral is completely artificial. Going back to mole.
What gets better is when you take samples, like measuring the pH of, say, your reactor coolant system, which is on the order of 600 degrees Fahrenheit and 2250 psi. I'm going to go ahead and use some non-metric units because that's what I'm used to, and it'll make this comment even more cursed, is the sample lines that go to laboratories are not at that temperature and pressure because it's kind of hard to get most instruments to function in those conditions. So are you really measuring the pH of the reactor coolant at that point?
The fact that we use a special unit for what's actually just a number isn't too weird. It's quite common for two units with the same dimension to behave differently because of context. For instance, hertz and becquerels are units of frequency that are both
Oh, he's bringing up becquerels.
equal to inverse seconds. The only difference between them is that hertz is used to describe periodic processes like waves, where the time between each event is the same, while becquerels is used to describe random processes like radioactive decay, where the time needs to be averaged over many events.
What's also weird is becquerels are such a small unit, because one becquerel is simply 1 disintegration per second. A curie is 3.7 times 10 to the 10th becquerels. I don't know if they're trying to say some statement about Curie's contribution to nuclear physics versus becquerel, but there you have it. Now, Curies are more commonly used in terms of like measuring liquid effluents. For instance, you'll see those numbers in Curies, but I think the main reason is because becquerels, you'd have massively huge numbers, because here you're talking about things on the atomic scale, whereas Curies are at least on a more macroscopic scale when you're looking at liquid effluent discharge limits for your nuclear power plant, for instance.
They're technically the same unit, but they have different contextual meanings, and so you would never conflate them.
Yeah, there's something per second, because yeah, disintegration isn't, you could argue that's not really a unit, or at least not an SI unit, because it's a disintegration, and a wave is just a different concept. Now, what can get really funny is when a disintegration results in a wave, say a wave from gamma radiation, so you can end up with per seconds per second. So kind of the opposite of meters per meters.
Now, becquerels originate from the study of radiation, and radiation dosage is another situation where you have multiple units of the same dimension measuring incompatible things. Grays and sieverts both have dimensions of joules per kilogram, that is, radiation energy per unit mass, but the former is absorbed dose, which is simply total energy, while the latter is equivalent dose, which has an extra factor depending on the type of radiation to describe how much it damages living things.
That's true. A sievert is a gray when you're dealing with things like gamma radiation, beta radiation, things that have very low linear energy transfer. That is to say, the gamma just passes right through you and doesn't impart much radiation to what's directly in front of it, and a lot of the energy is still retained as it passes through you. Compare that to an alpha particle. Here your multiplication factor is going to be 20. And that is a helium nucleus as opposed to a photon, which is going to impart quite a bit of energy to you, which is why it's multiplied by a factor of 20. So the point is, you do not want to take alpha doses internally, because while your skin will absorb most of an alpha particle by itself, if it's taken internally, it's going to do 20 times more dose than a gamma, for instance. Another example is a neutron, and it can depend on the speed of the neutron. A thermal neutron is about, or a slow neutron is a factor of 5, and a fast neutron, again, can get you into 10 or 20, depending on how fast.
Again, these units have the same
Target's
dimensions,
favorite color.
but you can't just interchange one for the other. However, the study of radiation does also have some redundant units. A rad, for example, is 1/100th of a gray, and they both measure absorbed dose. We could have just called the rad a centigrade, but no, it gets its own special name. The historical reason for this is the separation between two competing systems of units, the SI system and the CGS system. This is a whole can of worms.
Also, rads and grays are massive units, so you're most likely, and you mainly deal with dose equivalent in terms of radiation protection, so I should be saying REMS versus sieverts, but it's usually going to be microsieverts, millisieverts that you're most commonly going to see individual sources in, unless you're working with something really hot.
A can of worms that deserves its own section.
Dynes.
CGS is a system of units based on the centimeter, gram, and second. It was an old attempt at standardization that was eventually supplanted by the SI system, which instead established meters and kilograms as the base units of length and mass. But the usage of centimeters and grams is not the biggest difference between CGS and SI. The biggest difference is that while the SI system now has about 7 base units, CGS insists on describing everything in terms of centimeters, grams, and seconds, even when it reasonably shouldn't. This causes a big problem with electricity. First, I need to give some background on how we measure electricity. There's 2 ways that we could connect it to length, mass, and time.
I love it. Centimeters and grams of electricity. I know this is going to be good. I have not worked with CGS much, just to be clear.
The first is to look at the electrostatic force between 2 charged objects. This force is modeled by Coulomb's law, which we can use to define the coulomb, the SI unit of charge. The second...
Oh yeah, with epsilon being the permittivity of free space. I talked more about that in the previous rendition of cursed units, but I see it's all coming full circle now.
Is to look at the magnetic force between two current-carrying wires. This force is modeled by Ampere's force law, not to be confused with the two other laws named after Ampere, which we can use to define the ampere, the SI unit of current. Now, current is just moving charges, so we want.
So all these additional units are gonna, it's kind of like when you have, what this reminds me of is nesting all of these base units to force it to 3. It's like when you're nesting acronyms. And my favorite example of it in nuclear engineering is with the acronym AMSAC, called ATWIS Mitigation System Actuation Circuitry. And an ATWIS is anticipated transient without SCRAM. SCRAM being jokingly referred to as Safety Control Rod Axeman, or basically the reactor trip that safely shuts down the reactor in a couple of seconds. So, acronym within an acronym within an acronym, just to describe essentially a backup system to your normal reactor trip signals to say, hey, if the reactor didn't trip on these 10 different ways to trip your reactor, here's another one we're going to throw in there for good measure.
To define these in such a way that an ampere is just a coulomb per second, 1 coulomb's worth of electrons traveling through a wire every second. In order to do that, we need to introduce some physical constants to make the units work out, called the electric permittivity and permeability.
Oh, here we go.
But CGS works differently. In CGS, there are no constants, because everything is centimeters, grams, and seconds. The CGS unit of charge is the Franklin, also called the stat coulomb, which is the charge on these objects such that if they are placed 1 centimeter apart, then the force between them is 1 dyne, the dyne being the derived unit of force in CGS. Rearranging, we get the...
I've seen dynes on some bizarre scales before, but I never really knew much about them. I just kind of ignored it, because it looked pretty silly.
1 Franklin is a centimeter times the square root of a dyne. This approach is called electrostatic units, or ESU. Meanwhile, the CGS unit of current is the BO, also called the abampere, which is the current through these wires, such that if they are placed 1 centimeter apart, the force between them is...
Alright, I'm glad I didn't use this. CGS should be called the Cursed Grim System, or something.
2 dynes per centimeter of length because for some reason physicists have an obsession with throwing factors of 2 around. Rearranging, we get that 1 BO is just the square root of a dyne. This approach is called electromagnetic units, or EMU. Okay, we now have CGS variants.
I've heard of ESU, but I've never heard of EMUs. This is fascinating.
Of the coulomb and ampere. We know that an ampere is a coulomb per second, so naturally a BO should be a Franklin per second, right? Well, no. The units don't work out. A Franklin per second is a new unit called a stat ampere, a dyne to the half centimeter second.
Because of course, we gotta make...
And a BO second...
I think this is a classic example of you're trying to make something simple and then you inadvertently just make it more complicated.
Is a new unit called an ab coulomb, a dyne to the half second. That's okay, it just means that we need to multiply by some constant in order to get between these two schemes. This constant...
I also think seeing square root signs to the left of being multiplied by something is a little cursed, just because in my head I almost see the radical sign extending further outward, so I'm not sure if that dyne centimeter, if the centimeter should also be essentially raised to the half power, but maybe that's just my own weird visual behavior. But the point is, this is just getting really out of hand.
Must have units of centimeters per second, which means it's a speed. Can you guess what speed this is? It's the speed of light! This fact was discovered around the mid-1800s, and no one could make sense of it since the entire study of electricity was in a serious state of disarray, probably in no small part due to the confusion between the two variations of units.
So a stat coulomb is a cat coulomb. So a stat coulomb is a cab coulomb. So a stat is a cab that drives at the speed of light. This is ridiculous.
Just described. This was eventually disentangled in a series of papers by James Clerk Maxwell, who connected all of the results of the time into a single theory, which we now call Maxwell's equations. Using this theory, Maxwell derived a model for a wave of propagating electric and magnetic fields, and derived that the speed of this wave should be this ratio between the static and magnetic units, which by
I can only try to imagine solving an electrodynamics problem using Maxwell's equation with these units.
this point in time had been measured to be very close to the speed of light. It was already well known that light had wave-like properties, so this was the smoking gun that confirmed that light was in fact an electromagnetic wave. Now, that's a fascinating bit of history that's totally not cursed. But what is cursed is that the speed of light is 300 million meters per second. Sorry, CGS. That's 30 billion centimeters per second.
Yes.
Which means the two variants of CGS are different by 10 orders of magnitude. This massive disparity of scales is part of what makes electricity so counterintuitive. I think this is at the core of why electric quantities have all sorts of special names, unlike, say, velocity and acceleration, which are always expressed as derived units. In addition to amperes and coulombs, we have volts for voltage, ohms for resistance, farads for capacitance, henrys for inductance, Webers for magnetic flux, and Teslas for magnetic field strength. And each one of these units can be thought of in about 10 different ways.
So much easier. You can at least get it in one line. With the is it just going to show CGS? This would take like 10 pages of indiscernible mess.
To be honest, I respect the boldness of CGS, trying to reduce everything down to 3 units.
It's a good word.
It reminds me of Planck units, where you define the speed of light to have a value of 1, so that length and time collapse to the same dimension. And then you do the same with 3 other constants, and as long as you're consistent, you get a system that's entirely dimensionless numbers.
Planck constant.
These are pretty useful for simplifying calculations in certain parts of physics, but be careful, because if you pick different constants, you get different results.
Mainly see Planck units at stuff of the really big or the really small, really big, like cosmology, like in the context of Big Bang, inflationary models, that sort of thing. But also in high-energy particle physics, looking down to things that are really small, but things that are really small that are moving really, really fast. I've also sometimes seen Planck energy written out, but that's basically just Planck mass times c squared. So in this context, but that's basically just Planck mass times c squared.
CGS has for the most part been supplanted by SI, but it's still quite common to see centimeters and grams being used in a couple of smaller fields of science that like to bask in their old-fashionedness. Which leads me, of course, to materials science. I'm going to build...
seeing the STP written, something that's only valuable at standard temperature and pressure. So an atmosphere at 20 degrees Celsius.
For you a unit that only a couple of people suggested in the comments of the previous video, because only a couple of people know about it. This is going to be a unit for describing a property of a substance. So before I go into it, just as a warm-up, let me go through the example of heat capacity. Specific heat capacity is measured in joules per gram.
Okay, heat capacity shows up quite a bit. I know that one pretty good.
Degree C. So, given a certain number of grams of a substance, how many joules of energy do we need to put into it to raise its temperature by a certain number of degrees C? Each substance...
One of the reasons why water is used, because in nuclear power plants it has pretty good heat capacity.
...has its own number attached to this unit. For example, water has a heat capacity of 4.18 joules per gram degree C, while tin has a heat capacity of 0.21 joules per gram degree C. Make sense? Okay.
Right now I'm just in my head trying to imagine making a nuclear reactor out of tin. Or like liquid tin as your liquid metal. I don't think that would turn out pretty good.
Let's now build a unit to describe the diffusion of gas through a substance. How easy is it for air to get through a membrane? Well, the amount of air that gets through can be measured as a number of molecules, so we'll use moles, right? I'll use moles for now, but we'll come back to this later. The next thing to consider is surface area. The bigger the surface area of the membrane, the more air can get through. Let's measure this in square centimeters, so our unit is now moles per square centimeter. Make sense so far? The next unit is time. If we keep the air pressure on each side consistent, air will flow through at a uniform rate.
This is really just flux. So you look at neutron flux, for instance, in a nuclear power plant. Neutrons per square centimeter. However, in nuclear engineering, it's more commonly to use the term barn, which is 10 to the minus 28 meters squared. And you could think of it as and it's thought more so as a probability. Think of as a probability, and the term is used the term cross-section is used, and a barn being a microscopic cross-section. I mean, 10 to the minus 28 meters is pretty small, but the joke is about hitting the broadside of a barn with your neutrons. For example, uranium-235 has a cross-section of about 580 barns. So, pretty small target, but this is per individual atom, so you have many targets and many, many neutrons from fission. So that's a pretty big number, but it's a lot smaller than the cross-section for boron-10, which is 3,840 barns. So there's a reason why, on a macroscopic scale, when you emergency shut down your reactor using boron-10 control rods, it's going to stop your fissions very quickly, because this is all happening super, super fast, because these are going to absorb your neutrons because these have a much greater chance of absorbing your neutrons than your uranium-235, and they're going to shut down your fission reaction. So trillions and trillions of these events are happening in every fraction of a second. So this is just a fascinating way so each variation in your barns is going to be exponential, because it affects the stability of your chain reaction. Fascinating stuff. But thus far, I'm with them.
So our unit should be in moles per second per square centimeter. Okay.
Oh, actually, I misspoke earlier. This is more of a unit of flux, because it's divided by area and time. What I said earlier is the time-integrated flux. That is to say, it's not per second. It would be the total amount of accumulated over some period of time. That is fluence.
The next unit is thickness. The thicker the membrane, the less air will get through. This is an inverse relationship, so it goes on top of the fraction instead of on the bottom. We're going to measure the thickness in centimeters. Okay. I know a lot of people who watched the previous video are going to be shouting at their screen saying, "Cancel the centimeters." If you are one of those people, then I think you missed the point.
Yeah.
We saw that quantities like fuel efficiency and the Hubble parameter could have their units simplified, and that sometimes led to interesting results. But that doesn't mean we should simplify them. It's way more intuitive to measure fuel efficiency in gallons per mile than in square millimeters.
Gas per square millimeters? That's amazing.
And for the Hubble parameter, kilometers per second per megaparsecs is a direct description of how it's measured. At the end of that video, I mentioned that I used nanometers per square root nanometer in a research paper, and a lot of commenters suggested writing it as just square root nanometers, unironically. Yes, it's certainly interesting that you can write it as square root nanometers, but actually writing that in a research paper would be silly. I was trying to describe a relationship between two lengths, so why would I obscure that relationship by cancelling those lengths?
That's true, and that kind of brings back to the same point as energy per energy and like megawatt days per metric ton of uranium. I mean, it's usually presented in a report with Scrabble boards that show heat values, reactivity values, basically things that you hand to reactor operators so they have a sense of how the effect of how their control rods are going to behave at different times over core life, plus a bunch of other things.
It's fun to play around with units, but in practice, you should always use the units that best describe the physical quantities that they represent. Usually, it's the most commonplace units that are the ones that are best at doing this, the only exception being kilowatt hours per 1,000 hours, which is an inexcusable abomination. So no, we're not going to cancel the centimeters. You can do that in your own time, but right now we're building a sensible unit for sensible people. Right, the next thing to consider is pressure. If we increase the difference in air pressure between the two sides of the membrane, more air will get forced through. This turns out to be a linear relationship, so we need to put pressure on the bottom of the fraction. Now, the CGS unit of pressure is the bary, not to be confused with the bar, which is a million times bigger, but we're not going to use either of these, or the SI standard Pascal, because this is a sensible unit for sensible people. So we're going to use the only sensible option, centimeters of mercury.
There you go, centimeters of mercury.
What is a centimeter of mercury, I hear you ask? It's the amount of pressure that will push liquid mercury 1 centimeter up a tube. Great. This unit is a holdover from that time in history when we used mercury for basically everything.
Yep, and really can be in any fluid, but mercury is super dense. So, and mercury was used in the olden days because, well, you'd need about 14 times more water to put in your barometer. So, because a centimeter of mercury is about 14 centimeters of water. At the plant I worked at least for a lot of critical HVAC systems that support sensitive nuclear instrumentation, we'll have the pressure be in units of inches of water column. Again, because we didn't use the metric system very much.
Before realizing that it's both toxic and volatile. The best combination of properties. And finally, moles. We don't like moles. Moles are silly. So let's replace them with centimeters cubed STP, the number of air molecules that fill a cubic centimeter at some standard temperature and pressure. Oh, and multiply everything by 10 to the minus 10.
Because reason.
This is the bara, a unit of gas permeability used in the study of membranes, particularly
Definitely never heard of this one. Barer.
contact lenses. And I had to check through some research papers to make sure that this unit is actually used, because when I first heard about it, I was certain it had to be a joke. It contains 4 different variations of centimeters, 2 of which aren't even related to
Beautifully
length.
cursed.
And centimeters of mercury isn't even the most common unit of mercury. It's way more standard to use millimeters of mercury.
Yeah.
Which would be called torrs if they were the same thing, which for some reason they aren't? I've intentionally avoided talking about joke units like smoots or beard seconds in this video. I'm not just going to repeat Jan Mieseli's A Joke About Measurement. No, the whole point of this is to understand how we use units in practice, in the real world. And this monstrosity is a real unit used by real people. That being said, I do genuinely think the bara has its place. If it were completely absurd, people wouldn't use it. The main reason the bara is so complicated is that permeability is related to a lot of different factors. Sure, using centimeters of mercury and cubic centimeters STP is weird and esoteric, but even if we replaced everything with SI units, we'd still have something pretty cursed.
It's interesting because, yeah, there's a lot of things that feed into it. Going back to talking about neutron flux, pressure, it doesn't really matter because, I mean, the effects of pressure on something that small, a neutron, they're not really affected, and they're fast moving. It's not really relevant. Number is, surface area is, time is, thickness, not in the area you care about, because within the context of the reactor. What thickness is important, though, is how much shielding you put on your reactor vessel, and then, of course, your reactor containment building, in terms of making sure those neutrons do not escape and dose the public. And that's why material like concrete is so effective, because concrete is so effective, water is so effective, and concrete is hydrogenous material that effectively stops the neutrons from dosing people. Even inside the reactor containment building, there are certain areas you can't go in while the reactor is operating. There's an inner shield called the bio wall, or secondary shield wall, as some people call it. Secondary meaning the one that shields the reactor coolant system, as opposed the primary being the shielding for the reactor itself. Thickness isn't a factor within the fission reaction itself, nor is pressure. The pressure is really, the reasons why it's pressurized is for the water, and the water slowing down your neutrons so they can hit those targets.
Notation standards only make up half of the cursedness. The other half is the complexity of the science itself. There are so many other interesting ways units can get frighteningly bizarre that I haven't touched on yet, so there may be a Cursed Units Part 3 in the distant future.
That'd be cool.
Maybe then I'll finally talk about Imperial units.
Oh yes, this was another great one. I might have even liked more than part 1. Of course, I think I needed to watch part 1 first to fully understand the context, but man, this one sure was a lot of fun. Probably one of the nerdiest things just in general I've seen in a long time. And I mean that with the most amount of praise. Thank you so much for watching. I'll see you next time.